Hello everyone, my name is Natalie Rakowski and I'm a student at Georgia Institute of Technology. This is a video report on predicting the motion of falling objects using Newton's second law and kinematics of momentum in respect to gravity. We will discuss terminal velocity and how it is affected by drag force. Newton's second law is force is equal to mass times acceleration. Acceleration can also be expressed as change in velocity over change in time, as well as F net or net force over mass. If you expand out the equation for acceleration, you can find final velocity. Final velocity is equal to initial velocity plus acceleration, or net force over mass, times time. The integral of this equation is a position formula. It's a kinematic equation to describe position in respect to time. It is the change in the final position is equal to the initial position plus the initial velocity times time minus 1/2 the acceleration times time squared. I use this formula to predict how accurate the model was, or how accurate the formula was to how my actual experiment went. My experiment was I dropped a dry erase marker around 2.6 feet, less than 1 meter. That it weighed about. It started from rest, and it only weighed about 22 grams. The result of my experiment was the marker did not reach terminal velocity because the F net did not reach 0. This is most likely because I did not drop the marker long enough. But first of all, what is terminal velocity? Terminal velocity is the point in which the magnitude force due to gravity is equal to the magnitude force due to drag. Therefore, net force is equal to 0. At this point, the object falling moves at a constant velocity for the rest of its fall and does not accelerate. This is terminal velocity. So as you see here, this is the free body diagram of my experiment. There are two forces acting on my marker. There is gravity and drag. As you see here on my position versus time graph, as the object fell, it accelerated. It did not reach terminal velocity. If it would have reached terminal velocity, you would have seen a more linear pattern toward the end, but instead it stays an exponential graph. I had 12 frames. I was able to get 12 frames at a rate of 33 frames a second. That was 0.4 seconds worth of drop. So then I modeled my experiment in Tracker. I set this right here is the tracker model without drag. As you see, there's only one force, gravity. It overpredicts how far it should have fell. It said that it would have fell negative 1.4 meters instead of the negative 0.8 that it actually fell. That's quite a difference. As you see here, there's only one force acting on it, and that's gravity. I do not yet have the drag force added. And then over here, I have my model with drag force. There are two forces acting on the object, gravity as well as drag force. I did add in the drag vector. The vector is equal to b, an arbitrary constant, times the magnitude of the velocity of the ball squared. As the object falls, the drag force diminishes. And with a long enough drop, an object will achieve terminal velocity. So here is a comparison of all my scenarios. I have my tracker data and my model with drag are extremely similar, have extremely similar graphs. And then as you see, the computational model without drag it overpredicts, and it's quite off from what actually happened with my tracker data. As I said before, it did not reach terminal velocity. If it would have reached terminal velocity, you would see a much more linear graph towards the end of the drop. So the what if question was, what if I would have thrown my object down instead of starting it at rest? So I made a computational model of actually starting the object at a force of 20 newtons in the y direction. And as you see here, this scenario actually caused actually follows the computation model without drag. This is mostly because the 20 newtons cancels out the drag force. If it would have fallen for a longer period of time, it would eventually the drag force would have diminished the 20 newtons, and it would eventually reach terminal velocity. And so the conclusion of my project is that my object did not reach terminal velocity. There could be errors in my data, as you see here. I could have, in my tracker, I could have not actually had the points in the center of my marker. But so far, as you see, Newton's second law is a great tool for predicting motion of objects. Thank you for watching my video, and have a great day.